Okay, we're recording, and here we go. So last time we were talking about vector fields, and so just a real quick reminder, we've already done this, so I'm going to very quickly through this. A vector field is a function that to every point in the domain, it associates a field vector as the output that you think of as being a vector, and in particular that you think of as being an arrow with its tail at the point where you just evaluate. Okay, so it gives these kinds of pictures right here. We saw some examples last time, some sort of starter, easy examples, and then we saw a slightly weirder example. And of course, there's bazillions of different kinds of vector fields, and I can't draw pictures of all of them. But anyway, you kind of get the idea, hopefully, of how to draw these pictures. And I believe this is where we ended last time. Okay, so here's another vector field. This one, a weirder formula, but this is a very important vector field for sort of real-world reasons. Let me first describe the vector field. Here it is, this formula right here. Now, this is called a radial inverse square vector field. And I'm going to say that's a natural choice, but it doesn't look natural from the way it's written. Notice, though, you can rewrite it like this. All that happened in this rewrite is I took this three factors of magnitude and I kind of separated them out just a little bit. It didn't really do anything, right? But what you notice with this in this form is that is a unit vector, thus indicating direction, right? And furthermore, wherever you might happen to be, that unit vector is always pointing radially outward from the origin. Right, so thus the radial part of it all. And then, of course, you can look at the magnitude and notice that this magnitude is inverse square. And again, it tends to throw students when I say this is radial inverse square because they see the 3 here. And they think, well, isn't it inverse cube? But in fact, the magnitude is inverse square. Is everybody on board? Right. So who cares, and why would we be interested in such a thing? Well, there's a couple of really important examples. One is gravitational fields. Right? Gravitational fields are like this. This is how gravity works. So kind of a big deal, right? Now you may say to yourself, "Oh, come on! I'm going to spend the entire life that I live on the surface of the Earth where gravitational fields are constant. I mean, close enough." Right? So if you're not impressed by it being gravitational fields, maybe you'll appreciate that this is what electric fields look like. And those are decidedly not constant in everyday experience, right? If you're building something, what have you, electric fields are doing all sorts of weird things. And so being able to understand them is important. Okay. All right. Now I'm going to throw in an additional thought here that I think is worth noting. Both gravitational and electric being described by the same formula, different C, of course, obviously, right? The key observation I'm going to make here is that gravitational and electric fields actually look a lot like each other. And that's a really valuable observation for the following reason. If you need to study electric fields, and many of you do, right? There's something kind of weird about electric fields in the sense that, you can't see them, and we rarely experience them, at least, in a direct way that would allow us to get a handle on what they look like. But gravitational fields, very intuitive. We spend our lives walking around experiencing gravitational fields. So the fact that we have a huge amount of personal experience with gravitational fields, that experience you can use as intuition for understanding electric fields in certain senses. And I'm going to be making big use of this observation when we get into Chapter 7 later in the course. Okay. All right. Here is another example of a vector field. And I'm going to start off with something old that we talked about a while ago, gradients. Right? That's this formula right here. And we know that they always point uphill on the graph. That's all old news. Oh, I'm sorry, question.
Sorry, really quickly.
Yeah.
In both examples, it gets smaller as you go out.
Yep.
This is a function of C being less than a certain value?
Well, yeah, that's right. So these are pointing inward as I've got this drawn right here, even though the unit vector is pointing outward. And you're quite right. The point there is that this C is just negative for this picture as I drew it here.
Is there a difference if C is greater than 1 or less than 1?
Nah, not really.
Okay.
In fact, units will kind of mess up that question anyway. It depends on what units you're using. So yeah, but there's nothing of particular interest about the 1 is not an interesting point, but 0 is. It talks about the different directions. Yeah. Cool. All right. Okay. So what's the deal with gradients, and why are we interested in that concerning vector fields? The observation is, it is one. We didn't think about it that way at the time because previously, when we talked about gradients, the idea was we would, presumably be interested in a single point. We were looking at just one point at a time, and we would talk about at that point, what is the gradient doing, and what can we interpret about the shape of the graph at that point. By which, of course, I mean at the point on the graph. Above that point, remember we conflate those for convenience of language. So we were only looking one point at a time. But if you check out the formula here for this gradient, here's the gradient. We computed it out, and notice this is a vector field. This gives for every point x comma y, I get an associated vector. So vector field. So neat observation, a little bit of foreshadowing. It's going to turn out that gradient fields are actually particularly important vector fields. And how they are important and why is going to have to wait until chapter 6 and 7 when we'll be doing a lot of really important things with gradient fields. Okay, now a bit about language. Y'all remember, I assume, from Calc 1 classes that there is this thing called a derivative. And when you sort of reverse it, that's called an antiderivative. So I propose the following. If you are taking a gradient of a function, the thing that results should be called the gradient, of course. It's a silly observation. What could be more clear? That said, how would I describe this thing? Well, this is the thing that when I take the gradient of it, I get capital F. Or said differently, shouldn't I call little f the anti-gradient of big F? And that is my favorite choice of words anyway here for how to describe this function f. It's motivated, again, just like derivative and antiderivative. Right? I think it's very natural language. That's what you're going to hear me saying in Math219 when I'm talking about such a thing. Now, that said, I do want to point out this is not the most common term. The most common term to describe this is potential function, which seems to come out of nowhere. Right? Where it comes from is this right here, this fact. There is a relationship in physics between potential energy and forces. And so, okay, cool, that's the deal. This is just how physics works. Take a physics class if you want to hear more about this. Right? But the unavoidable problem, as I see it anyway, is that there's this minus sign here. And that minus sign is important. And roughly speaking, it goes like this. Forces point towards lower potential energies. Gradients point toward higher potential energies. The more casual parlance, gradients point uphill. Forces pull you downhill. Right? So it's just that they are unavoidably opposed to each other. So to me, I find it very awkward that they would like to call this function a potential function because, check it out, it isn't potential energy. It's the negative of potential energy. So I think that's weird and confusing, and I've always disliked it. But nevertheless, it's very common terminology, so heads up, and good luck. All right, any questions about that before I go on? Okay. All right. Okay, so we've seen a bunch of forces. that can be represented with vector fields. I want to point out, and we're going to do several observations with how vector fields can be used to represent fluid flows. This is another situation where at any given point you can associate a vector, which is what a vector field is. Now, some real-world examples of fluids flowing in 3 dimensions. Here's some, I rattled off a couple of quickies, right? But for example, how the air is flowing in this room, right? The air in this room is not stationary. The AC is blowing air out of one of those things in the ceiling, and air is coming, being pulled into one of the other things there. So there's a certain amount of air flowing around. And at any given point in this room, right, say this point right here, if I had the equipment to do it, I could measure what the velocity of the air is. At that given point, what is the velocity of the air? And as such, at every point, I have a vector. That's what a vector field is. Right? Does that make sense to everybody? So the flow of a fluid in general can be represented by a vector field. Various other examples. Now, these are all basically flows of fluids, just different kinds of fluids in different kinds of contexts. Now, these are 3-dimensional. There are, however, 2-dimensional fluids, and you don't even need too much imagination to visualize these. It's not like we have to go to a parallel universe that's 2-dimensional. It's as simple as thinking about things flowing on a surface. Right? So it's actually pretty easy to visualize. I like to point out, in particular, that animal migrations you can think of as a flow of a fluid. And it seems weird because wildebeests don't seem to be fluids, right? But that's just a perspective thing. That's because you get too close and they don't seem like particles, right? But if you were to go up to a satellite, right, and take a photograph from way up above of a herd that has, I don't even know how many they have, hundreds of thousands, right? Something like that. What you would notice is that flow seems kind of fluid-like. And basically, a herd of hundreds of thousands of wildebeests seems like a bunch of particles kind of moving as a fluid. And if you think about it, water itself, right, the fundamental fluid of our experience, is made up of a bunch of little teeny tiny little particles that kind of flow together. So I think it's actually very reasonable to think of a herd, right? Or if you're talking about birds, maybe a flock or whatever, as kind of in a way being a fluid, and as they move, we can describe it with a vector field. What do you think? Is that cool? Okay, so now we're going to do a calculation. I think this is an important calculation. By the way, a lot of the stuff that we're doing in Chapter 3 is kind of preliminary for Chapters 6 and 7. Bunch of important stuff is going to happen in Chapters 6 and 7. What this calculation is right here is going to come up very valuably in Chapters 6 and 7. So why are we doing it now, right? Why in Chapter 3? And the reason is to allow these ideas to kind of stewing inside of your head and allow you time to kind of digest and get accustomed to them, so that it's not just a bucket of cold water in the face and then we immediately start doing things with vector fields. Just to give you a digestion time. And this is such an example. So I'm going to start off with a vector field representing the flow of a fluid, specifically by way of the velocity. I'm going to point out that while this is a natural way to describe a fluid with a vector field, it's not the only way to describe a fluid with a vector field. There's another one that I'm going to show you all in a couple of minutes. But anyway, for this example, vector field is velocity. Okay, and I want to ask the question, and I was going to get into this mode. There we go. I'll do it like this. Oh, look at that, it all fits. So suppose I have an area, right? My area has a certain amount of size. In other words, there's an area to this surface, right? And there is a normal vector, a unit normal vector, called N. We use unit normal vectors to represent how areas sit in space. It's like if you look at my hand represents a piece of area, right? A flat piece of area. But there's lots of ways that a flat piece of area can sit in space, right? And notice that however I might do my hand, the normal vector tells you how that area is arranged. Right? So very handy little trick. Single vector, typically a unit vector, tells us about the arrangement of an area in space. Okay, so reasonable question. If I have a fluid flow like this, that's telling me velocity of the fluid. But how would I get my hands on the flow rate through this surface? Velocity is in terms of feet per second, right? But flow rate, I want to know how many gallons per second, right? Or cubic feet per second, or quantity of fluid in whatever sense per unit time is flowing through my piece of area, right? So the velocity of the fluid, not the same question as the flow rate through an area. Does that make sense? Everybody see the difference there? Right? So I want to know, how are we going to compute dV dt? So the big idea here, let's see here. I was going to use yellow here. Let's talk about how much fluid, volume of fluid, flows through my surface in any given amount of time, delta t. All right. So we're just going to directly compute this amount of volume. I appeal to your physical intuition. If the fluid is going that way, then the fluid that has flowed through this area will be represented by that little parallelepiped. Okay. All right. So here we go. Let's see. Volume is height times area. Now that's high school geometry, right? Height times area. Height times the area of the base. It might be the way you've heard it. Okay. Let's talk about that height. It's going to relate to this vector here that I'm going to call, I wanted to be in pencil mode. Sorry. Let's see here. It's going to relate to this vector here. I'm going to call that d. That represents displacement. Now the amount that a given piece of fluid has been displaced in our amount of time, delta t, is something we can write down a formula for, and we'll do that in a second. But notice the height relates to that displacement, and in particular, the height is just the component of the displacement in that normal direction. Flashbacks to chapter 1. Components, of course, are computed with dot products. So we get that. Okay. Then let's talk about what this displacement vector is. This displacement vector, let's see, now I want to be in the highlighter mode. This displacement vector here, how much does the fluid move in a particular amount of time? Well, we know the velocity. The velocity is the vector field. And displacement is velocity times time. So this displacement vector in green, velocity times time, right there, delta t times f. Okay, is everybody on board so far? All right, so now I've got a colorful picture here, which I'm going to clean up a little bit. I'm going to erase most of what we've got here. In fact, why don't I just erase everything? And let's see, keep in mind, we want to know flow rate, so volume per unit time. Let's see, how are we going to represent time? Well, time is this delta t there that we're taken the derivative with respect to. It's the amount of time that it took for this picture to sort of get created. And so altogether then, this object that we're interested in, volume per unit time, is this thing right here, right? F dot n times A, that's just what's left over after we sort of divide through the dt right there. And this is what we call flux. It turns out this expression, flux, is natural in a couple of really, really handy ways. And this is the first one of those. This expression, F dot n times A, tells me, if my vector field represents velocity, it tells me my flow rate. Very natural, physically natural. Thus the name. By the way, we also have a notation for it. This is the capital Greek letter phi, and a pretty common choice. Capital, mind you. Lowercase would be a spherical angle, right? We don't want to conflate this with a spherical angle. So capital phi to represent flux. All right. So now there's a related question. The related question is, what if I have a different way of representing a vector field? What if I use not velocity, but seemingly weirdly density times velocity? Seems a little strange at first glance, but what if I use that to represent my vector to represent my fluid flow, and that in particular, that's what our vector field is. Why would I do such a thing? What does this buy me? And the answer is, the reason we would do that is because then if you compute this thing called flux, again, the same exact expression that we previously had that previously told us volume per unit time. In this situation, flux will compute mass per unit time instead of volume per unit time. And I think this is a really nice exercise. I want to encourage everybody to take a crack at this. I'm going to walk you through a way of thinking about this, how to get started. Keep in mind that when we computed volume per unit time, our first step was to write down a formula for volume. Right? So, well, if I want instead to compute mass per unit time, the very first thing I need to do is to write down how much mass is there in there. And the thing is, mass is density times volume. And we've already written down a formula for the volume. So let's just throw in that extra factor of density, and we get to reuse a bunch of information that we already had. Notice this factor of density. It looks like I'm doing it for you all after all. This factor of density just kind of goes all the way on down there. And then at the very last step, density gets absorbed inside of the vector field where you see it right there. So anyway, that's how that works. I know that's very, very quick. I think it'd be a good exercise for y'all to think through and make sure that you're comfortable with all those details. Think how this happens at the end. Make sure you're comfortable with that. Okay. So altogether then, we actually now have two pretty great motivations for why we'd be interested in this thing called flux. We're interested in flux, aka this expression, because on the one hand, when the vector field represents velocity, it gives me volume per unit time. And on the other hand, when the vector field represents density times velocity, it gives me mass per unit time. I have two very desirable quantities to understand. Both are computed by the same expression called flux, just making different uses of the vector field. So, neat fact. Okay, and tremendous applications in physics and engineering, and far more than this as well. Okay, now the next page here. This is a supplemental page. I'm going to talk about some of this, but supplemental stuff. I mean, I do what I can when I can. We're a little behind schedule at the moment, so I'm not going to be able to do this whole page, and I'm going to kind of just wave my hands at most of it. But I want to address an awkward matter and point out that there is a way around the awkwardness. So we've talked previously at some point about the idea of a light bulb generating a fluid flow. And so, for example, let's think about this little point right there. Imagine that's a little LED, and it's emitting light in every which way. And I can talk about that fluid flow, right? The flow of photons, and I can talk about at a point like, let's say right there, and the velocity of the photons, maybe something like that, because at that point, that's the path that photons follow, and it's going along that path. So it's perfectly easy to describe the velocity of the fluid there. Okay. Where things get awkward is if I have two or more point sources. So let's suppose now we have two. So I have an LED there, I have an LED here. They're both emitting a flow of photons, a flow of a fluid. So I've got all this fluid flowing around, and I can reasonably ask the question, what's the velocity of the fluid, let's say, at this point? And the problem is, the photons that come out of there have a velocity that looks like this, and the photons that come out of here, anyway, you know what I meant, have a velocity that looks like that. Which one of these, perhaps, should represent the total sort of fluid velocity at this point? And I point out, well, neither one. Some photons are literally going this way, and others are literally going that other direction. There is no single velocity that I can talk about if there are 2-point light sources. Is everybody okay with that? Everybody see what I'm talking about? So what do? Can I not represent this by a vector field? Sure was handy on the previous page. Here's a way around it. The idea is if I can describe velocity with a vector field, so let's assume that I have the vector field, then I can answer questions about how much flow rate of stuff is there through any given piece of area. Right, you give me an area and an orientation in, and knowing the vector field, I can compute this, and that tells me stuff per unit time flowing through area. What we're going to do here is just turn this around. We're going to keep the formula and say, look, I can empirically measure flow rates. Right? That's an observable. Now, the actual mechanics of that, how do I actually measure the flow? That's a practical problem. That's an engineer's problem, right? It's not my problem, right? But you could, for any given piece of area, just literally ask the question, what is the total net flow rate of material through your area? And then you can reverse engineer and say, look, there's only going to be one vector field that I could put there that would make this formula work for all the areas and all of the orientations, etc. And so we would define the vector field to be whatever it is that makes its equation. So it's a nice point of view. This is gets used in many different circumstances. Okay. All right. By the way, before I go on, I'll point out that there was something even in this case kind of simplified from reality. I assumed that I had 2-point light sources. Let's think about the point light sources in this room. How many light sources are there? There's a bunch of bulbs, there's a projector, there's a bunch of light bouncing off the screen. Photons coming from this part of the screen are not going the same directions as photons that are bouncing off of this part of the screen. Light is furthermore bouncing off of the walls and all the people, and oh my God. Right? In this room, at any given point, there's light going all sorts of every which way. And there's absolutely no hope of being able to associate a single velocity to the flow of photons. But you can do something like this. This example that follows is cool, and I wish we had time for it, but this is highly supplemental. It's not something we need to do, and being behind schedule, we're not going to. You are encouraged and welcome to check it out, and if you want to come to office hours and ask me questions about it, I'd be very happy to talk about it. But like I say, we just don't have time, and it is totally supplemental. Yeah.
For the one before, what is A?
So N is this, what we call the normal vector, describing how the thing is oriented. Remember I was doing like this? N is this vector that helps me understand how the area is sitting in space. And is it like this, or is it like that, or is it like this?
So is it perpendicular to the...
Yeah, it's this right here. So the normal vector, that's right, is perpendicular. Normal typically means perpendicular to the area. Yeah, totally.
And it can be on like any part of the area, like
Yeah. Here I'm assuming it's a flat piece of area, and so yeah, it can be. It doesn't. All of the surface is perpendicular to the same vector.
Okay.
Yeah. Okay. So moving along, we need to talk about what's called a flow line, and this is a casual use of the term line. Flow lines are typically not lines; they're typically curves. A flow line is the answer to a certain natural question, and that is, if you have a fluid flowing around, the fluid flow might be somewhat static, right? It's just kind of always the same. Like you look at the water flowing in a river, it's pretty much the same now as it was 10 seconds ago. It just doesn't really change that much that fast. So if I were to toss something into the river, what path would it follow? Right? Pretty reasonable question. And the answer to the question is surprisingly straightforward. If your vector field represents the velocity, and if the particle is doing exactly what the fluid says it should be doing, then the velocity of the particle, if you think about it, right? What is the velocity of the particle? Velocity of the particle is exactly the same as the velocity of the fluid, because the particle is following the fluid. The fluid is what is pushing the particle around. Right? And of course, the velocity of the fluid is the vector field. Now, one last little detail, the fluid flow, again, it's very different over here than it is over there. Right? So when I say the velocity of the particle is equal to the velocity of the fluid, of course I mean the velocity of the fluid where the particle actually is. Because it's where the particle actually is that the water is pushing it. Right? So I think if you break it down in this way, it's kind of immediate that the velocity of the particle is the velocity of the fluid at the point where the particle is, and you get, therefore, this equation that says that x prime is f of x. And now, just for cleaning up purposes, let me get rid of all of this. And this is what we call a system of differential equations. It's a system because the velocity is vector valued. There are several coordinates there. The vector field is vector valued. There's several coordinates here. So each one of these, what we call systems of differential equations, is actually literally a bunch of individual coordinate differential equations that are all linked together. And it's a trick as to how to solve those. And the trick for how to solve these kinds of differential equations is not a topic of this course. That's a topic of Math 353 for those who are Pratt students, or Math 356 if you're math or physics major. And they'll talk in those classes about how to solve these. Okay. What do you think? Everybody cool? So we're not going to be solving these differential equations in this class. We will, however, be confirming solutions that have been provided for us. And that's what this example is here. The example says, suppose we have this fluid flow right here. I hope y'all might recognize this vector field. We spent a little bit of time last time talking about this vector field. This is the one that's, I like to think of it as a stirred pot, right? The fluid is kind of going around in kind of circles like this, right? Does that look familiar? So this vector field, I mean, let me just scroll back to it, in fact. Here it is. Yep, see? Stirred pot. If I were to drop a particle of some sort, let's say right there, what do you suppose would happen to that particle? If I dropped a bay leaf into my pot on the stove that I've stirred, right? What's the bay leaf going to do? Well, I mean, I think it's pretty believable. It's going to kind of go around in a circle, wouldn't you figure? So on that basis, we speculate that maybe cosine t comma sine t might be a flow line for this vector field. Now, how would we confirm this? Correction, how are y'all going to confirm this? Y'all are going to confirm this by way of this equation that we just talked about, right? Where this is the vector field F that you plug in, and you, on speculation from our intuition, you're going to plug in this parametric curve in for the x, and then you're going to do exactly what the equation says. On the one hand, you're going to take the derivative of the parametric curve. On the other hand, you're going to take the parametric curve and plug it into this vector field. And then you're going to confirm that as it should be, these are the same. That make sense? A nice little exercise. Give that a shot. It's very quick. Should be no trouble. And there is at least one homework exercise where you're going to do something comparable to this. Yeah.
Sorry, for the first side, you would just like take the derivative.
Yep.
Okay.
On the left, it's literally, so this is x. And then note the left-hand side is literally just x prime. Okay. So, no problem. Yeah, no worries. Okay. All right. So, a real quick note, I over the years that I've been teaching multi here at Duke, I've noticed certain constant mistakes that students will make, right? And I like to try to head those off before they become problems. One of those mistakes is a fair number of students will take all that we've just talked about, and keep in mind we've talked about vector fields as representing forces, and we've talked about vector fields as representing fluid flows. And very often students will sort of pick one that they like, and they'll be like, all right, this vector field stuff is weird. I'm going to always think in terms of fluid flows. It just seems to make more sense in my head, or something like that. Maybe forces if you prefer. And I just want to point out, you can't do that. You can't make a choice. We're going to need both. And this is going to be critical to the applications that we're going to be making. And not only is it critical to applications, it's critical to getting good sort of mathematical intuition for calculus that we're going to be doing in Chapter 6 and 7. And it's hard to see that coming right now, but I'm going to ask you to take my word for it. That is going to be essential. So please do not just pick one. That's a bad plan for Math219. Make sure that you get good intuition for both of these, what I call metaphors for vector fields for going forward. Okay, 3.4. This is a weird section. It's arguably premature. We're going to be talking here in section 3.4 about stuff we're not going to really fully develop until chapter 7. So why are we seeing it in chapter 3, one would naturally ask. And the reason is, this is just kind of a pedagogical thing, but it's so you can have time to sort of chew on these ideas. There's some weird pictures that we're about to talk about. And even though we won't be really fleshing it out completely right now, we don't have the tools right now. It is a healthy thing for you to kind of get accustomed to the sort of the weird geometry and weird intuition that we're going to need to have when we get into chapters 6 and 7, especially 7. So I'm going to introduce, by the way, and of course also the book does this, so we need to do it anyway, but it's a good idea. We are going to talk through some of these ideas. I'm going to make some assertions that are going to be completely unjustified. And I'll clean that up later, right, in chapters 6 and 7. For now, I'm just going to make some assertions. I hope you'll trust me that these assertions are reasonably valid, and then we'll get precise with it later on. Okay, so here we go. Let's see here. Y'all remember the gradient, of course. Here's a weird way to write it. It seems strange to kind of, if you will, kind of sort of factor out the f, right? But if if you were to try to make sense out of this thing, wouldn't it stand to reason that you would, of course, take the x partial of f, and then you would take the y partial of f, and then likewise the z partial. So this is a reasonable alternative notation. And having written the gradient like this, it's also reasonable to take, let me use blue, this thing right here, the thing that we're doing to f, and say that's what this is. And we're going to consider this a standalone, separate object called an operator, right? And it itself, this isn't really a function, this is something I do to a function. And so del, as I have it drawn here, del is something that I do to f to produce this thing called the gradient. Okay, is that cool? Is everybody all right? As a point of language, a lot of students get confused. Why won't we call this the gradient operator? And it's because we're going to do various different things, not just gradient, with this operator. So we need a sort of an independent name so that we can interpret it as applied to other constructions. Okay. All right, and here's the first one. The first one is called divergence. Divergence of a vector field. So given a vector field, it has coordinates f1, f2, and f3. Okay, let me do it like this so I can keep everything on the screen. f1, f2, and f3. This formula right here, weird though it looks, x partial of f1, y partial of f2, z partial of f3. Kind of weird. Why would I do that? Where does this come from? Yeah, I can't tell you right now. Right? We'll talk about that later. Turns out it's really important, really natural. And you'll notice also that the del operator kind of makes an appearance here. You can see the del operator in, well, there's the x partial and the y partial and the z partial. And it's like I took the first coordinate of del and applied it to the first coordinate of f, and then the second to the second, and the third to the third, and then I added them up. It looks exactly like a dot product. So this is extremely common, extremely natural notation. We write this as del dot f. So now, it's a little bit of an abuse, right? Dot product is supposed to be something we do to two vectors. This is not really a vector, right? But if you are willing to just kind of be a little forgiving about the abusive notation, dot really fits really nicely. Is that cool? All right, so divergence. What does this look like? How do we think about it? What can we do with it? Why are we wasting our time talking about this thing that I seem to have made up out of nowhere? Again, full disclosure, we are not really prepared to have a full conversation about this yet. So again, apologies, and again, trust me. It turns out, here's the answer. Divergence represents roughly speaking, the amount that the fluid is flowing away from where we were looking at. To what extent is fluid flowing just kind of generally outward as opposed to generally inward or something like that? And I know that's very hand-wavy, and we'll make this more precise again in chapters 6 and 7. So here is an example. Here's a vector field. I'm going to let you all think through how the picture of that vector field would look something like this. You may recall that we've seen a vector field that looks almost exactly like this before, in particular where the field vector is the position vector for the input point. Right? And this the difference is that this is now three-dimensional, so the picture would look something kind of like that. Is that cool? Okay, so let's take the divergence. And we can totally do this. I'm going to literally take the first, second, and third components of my vector field and take their partials with respect to x and y and z, and in the sort of the dot product sort of way. And as a result, my divergence being the sum of three easy partials, as it turns out in this case. My divergence is 3, which you'll notice is positive, which means we have to some positive extent, the fluid is flowing kind of away from where we were looking. We were looking at the origin. So that tracks, that's consistent with the picture that we already have of a fluid kind of flowing away. Is that cool? Now, this doesn't prove anything, right? You should not right now be looking for having convinced yourself that this demonstrates the picture or demonstrates the relevance of the formula. This is just a kind of a, hey, see, check it out. It operates as claimed, at least in this one case. Okay. Now, there is a natural physical question to ask here, which is, what is this representing? And the reason I bring this up is because there's a couple of pretty good answers to this question that are very independent of each other. This picture right here could represent a fluid where there's a certain amount of fluid near the origin and all the fluid starts flowing outward for some reason. Why it would do that, I don't know. It depends on the circumstance. But if there was a certain amount of fluid in here, a certain amount of fluid density, and if the fluid starts shooting outward away from there, then the amount of fluid in that general vicinity will be going down. And your fluid density should be decreasing. Does that make sense? Everybody okay with that? Yeah? Okay, so that's one interpretation. Maybe that's what this is a picture of. On the other hand, here is a perfectly good alternative physical interpretation. It could be that there is no loss of fluid at all. It could be that this is a picture of something in the vicinity of the origin actually generating fluid. And again, my favorite example is this light bulb, because it's pretty relatable and pretty intuitive that if you have a little LED right there at the origin, it's shooting out photons, but it's not like the LED has like some supply of photons that it'll eventually run out of, right? It's literally making photons, right? So these two possible interpretations, notice, are inconsistent with each other, right? If you have a light bulb, you're not losing photon density, right? And it is perfectly possible for fluid to be moving away from some general area without it being spontaneously generated. It's just, no, the fluid was there. It decided to go away. Right? It doesn't mean you're making fluid. So when you're thinking about a particular instance of a vector field representing a fluid flow, and you're talking about the divergence, and you're going to make an interpretation of what divergence means, you need to study your fluid. And you think, what kind of a fluid is this? And which one of these should be the right interpretation in that circumstance? And we'll talk more about that in Chapter 7 as well. Okay, another example. This is just another, again, for example. Here is a vector field. Y'all can persuade yourselves, good exercise, that this formula generates this picture. Right? Good one to think through. Make sure you're comfortable with that. You can compute the divergence in the usual way. And the divergence ends up being 0. So from a fluid's point of view then, what that's saying is that this is, there's no outward flow. Keep in mind, divergence is supposed to represent the extent to which fluid is flowing outward. Well, there isn't any. It's not like it's negative, which would mean an inward flow. It's not positive, thus an outward flow. It's just there's no net sort of flow in or out. And I think that actually tracks very satisfyingly with the picture. If I look at this little vicinity right there, well, there's just as much fluid flowing in as there is fluid flowing out. So in the net, in total, 0. Is that believable? All right. Next, we're going to talk about something called curl. This one, again, I'm going to pull out of nowhere. I'm going to write down a formula that I don't justify and won't justify until much later, right near the end of the course. Again, presuming I have a vector field, and the way we compute the curl of the vector field is this wacky formula right here. Notice that my vector field, wrong color. My vector field makes up the bottom row. My del operator makes up the second row. And notice all that remains is to make sense of what do I mean by a cross product. What an odd notation, right? Again, we have to, be flexible in our interpretation of the cross product. It's supposed to be for two vectors. The del operator, you got to kind of, be flexible, be willing to interpret this as a vector. And cross is what you get when you, again, determinant and then standard basis vectors across the top as our little symbolic determinant, and then first vector in the next row, second vector in the last row. So this is just literally, right? I mean, if I were to ignore certain rules, this is just literally what this cross product of those two things should be. And we call that curl. Okay, why? And what does this look like? And again, full disclosure, we're not even close to being able to make any sense out of this yet, right? So again, you just have to take my word for it. And the answer is that curl represents, in some sense, how a fluid is I'm going to do some hand waving and some flexible language here. I'm going to say circulating around a point. And that's not really quite right, but I'm going to fix that in just a minute. But roughly speaking, curl represents the extent to which a fluid is circulating, kind of like in this picture here. Now, y'all will recognize that vector field. It's a little bit of a twist on a vector field we've seen before. It's a sort of a three-dimensional version, but you see the minus y comma x. This is the stirred pot. Again, it's just that now this is a stirred pot in 3 dimensions, and it looks, something kind of roughly like this. So the curl, if you compute it using the usual formula from above, turns out to be 002. And notice this vector is telling us in some sense how this fluid, the water in this stirred pot, how is it kind of, if you will, sort of circulating? It's circulating around that curl vector. And in fact, that's how this is how curl describes what you might call a rotation of a fluid. Thumb in the direction of the curl of your right hand. Sorry, it's got to be the right hand. Thumb in the direction of the curl. Fingers pointing in the direction that the fluid is kind of rotating, if you will. Yeah.
So the vector that you wrote as like the z-axis, is that vector 0, 0, 2?
Yeah. The curl vector is Yep. That's right. Okay. Yes.
Is there a case in these when like if you take I guess if the f was more complicated, because every time if you do the derivative of y over the derivative of x, you just get 0.
Mm-hmm.
So there's cases when it'll be more complicated. Where you
Yeah. No, these are easy, sort of first glimpse kind of exam. Yeah, they won't always be constant like this. That's right. Yeah, exactly. Okay, let's see. Are we out of? It looks like we're probably out of time here. Yeah. Oh, I'm sorry. We are absolutely out of time. Okay, so we will draw the line right here, and we'll pick up here next time. Okay, see y'all later.
I'm sorry, I was driving this.
Oh yeah, no worries. That's fine. Not a problem.